Now let's have a look at the LTE technology basics. This slide provides an overview of LTE key parameters. First of all, the frequency range for LTE. So LTE can be operated in the FDD and TDD bands of UMTS. So on the next page we will also see what these frequency bands are in detail. The channel bandwidths for LTE. So there is bandwidths defined 1.4 MHz, 3 MHz, 5 MHz, 10 MHz, 15 MHz and 20 MHz. And each bandwidth actually is composed of a certain number of resource blocks. As you can see in this table, a resource block is defined to be 180 kHz each, and the resource block represents the smallest entity for a resource assignment. So a terminal or subscriber can be assigned one resource block or multiples of it. And this is true for uplink and downlink. So 1.4 MHz actually is represented by 6 resource blocks, and so on up to the 20 MHz being represented by 100 resource blocks. Modulation schemes that are available for LTE are QPSK, 16 QAM and 64 QAM, where in the uplink the 64 QAM is optional for the handset to support. Multiple access schemes for LTE are the OFDMA in the downlink, orthogonal frequency division multiple access, and single carrier FDMA in the uplink. LTE supports the MIMO technology. Actually, MIMO, multiple input, multiple output antenna technology, is very essential for LTE in order to support the high data rate and throughput requirements. In downlink, a wide choice of MIMO configurations is possible for LTE, and there's different MIMO modes supported. For example, there's transmit diversity, spatial multiplexing, cyclic delay diversity, and we can have a maximum of 4 antennas as the base station, which is defined in the standards, and also maximum 4 receive antennas at the handset, which is of course quite challenging. In the uplink, a multi-user collaborative MIMO is supported, so several users can share the same resource block assignment. We will see a detailed introduction to the MIMO at a later part. LTE peak data rates in downlink, we can achieve 150 megabit per second with a 2x2 MIMO configuration, which would actually be represented by UE category 4. And we can even achieve 300 megabit per second peak data rate in downlink with a UE category 5, which would stand for the 4x4 MIMO setup. Both values are true for 20 MHz operation. In uplink, 75 megabit per second peak data rate in 20 MHz operation are possible. So please note, the peak data rates are really more theoretical values. They are not likely to be achieved in real life scenarios, because in real life you have certain cell load, you have certain radio link situations, which will not allow these data rates for a particular user. So nevertheless, the peak data rates are always quite useful to see, because they give you kind of a reference of what's theoretically possible with the system. So this table shows the LTE frequency bands that are specified. The table is actually taken from 3GPP specifications as of March 2009, and they are showing the specified bands for LTE operation. So there will be more bands added in future. For example, there's the work on UMTS LTE 3.5 GHz operation ongoing. So as you can see in the table, the bands 1 up to 17 are defined for FDD operation, and the bands 33 up to 40 are defined for TDD operation. There's some prioritization already defined, so there's a certain prioritization for bands 1, which is the existing UMTS band, band 3, band 7, which is the 2.6 GHz band, and band 13 in the 700 MHz arena. For TDD, band 38 and band 40 have a certain prioritization for real network deployment and for the first commercial deployments. But in principle, LTE can be operated in all these frequency bands. So now let's have a closer look into the OFDMA multiple access scheme and the downlink frame structure for LTE. So what is OFDM? In an OFDM system, the available bandwidth is subdivided into multiple subcarriers. And each of these subcarriers can be independently modulated. So typically you have several hundred subcarriers in a certain bandwidth, and they have a constant spacing of some kilohertz. The figure shows an example for the 5 MHz bandwidth, and you see the subcarriers. But of course, you can easily scale the OFDM principle also to higher bandwidths. Like in LTE, you have up to 20 MHz bandwidth. So compare the OFDM transmission with a single carrier transmission, for example for wideband CDMA. Since the multiple subcarriers in OFDM are transmitting in parallel, each one can transmit with a lower symbol rate, thus improving robustness of the technology for mobile propagation conditions. This picture shows the OFDM signal generation chain. So the modulated data symbols, which are going to be transmitted, are first parallelized, and then they are used as input bins to an IFFT operation. IFFT stands for Inverse Fast Fourier Transform operation, which is taking place on the transmitter side in an OFDM system. This operation produces OFDM symbols. So actually we have a conversion from the frequency to the time domain here, and the OFDM symbols are then transmitted in the time domain of an OFDM signal. To each OFDM symbol, a cyclic prefix is appended as a guard interval to protect from inter-symbol interference. So this also means that with a longer cyclic prefix, radio channels with a larger delay spread can be addressed. So for example, larger cell, you would expect a larger delay spread, and therefore a configuration with a longer cyclic prefix would be helpful. On the receiver side in OFDM, you would expect an FFT operation to receive the symbols again and to convert again in the frequency domain. Now, what is the difference between OFDM and OFDMA? We have seen both terms already. So in OFDM, the users are allocated in the time domain only. So in this picture, you see on the y-axis the frequency domain and on the x-axis the time domain. And you see that user 1 has been assigned the full bandwidth, user 2 as well, and user 3 as well, and they are only separated in the time. Compared to that, on the right hand side in OFDMA, the users are allocated in time and frequency domain. So you see that user 1 is only using part of the available bandwidth, as well as user 2 and user 1, they can share the available bandwidth to a certain extent. So this is actually a very flexible scheme, therefore it is also used in LTE, because you can also, for example, exploit gains of frequency-dependent scheduling. So you could exploit the fact that user 1 has a more beneficial radio link quality in a certain bandwidth area of the available bandwidth. So LTE uses a conventional OFDMA scheme. The picture shows an example for 5 MHz bandwidth, but of course you could also extend it to the other bandwidth values and scale it accordingly. So you see here the representation of the signal in the time and in the frequency domain. In the frequency domain, you see here the subcarriers represented. In LTE they have a constant spacing of 15 kHz for the regular configuration of the signal. And as we have seen, so you can transmit now and independently modulate on each of the subcarriers. The orthogonality of the subcarriers is also illustrated here. So in terms of the function here of each of the subcarriers, the frequency function, you see that where one subcarrier has a maximum, all the others have a zero crossing, which means that this is representing the orthogonality of the OFDM signal. In the time domain, you see the OFDM symbols transmitted, separated by guard intervals. In LTE, also we have a cyclic prefix as guard interval. Different configurations are possible. We have a normal cyclic prefix with 5.2 microseconds for the first symbol and 4.7 microseconds for the other symbols of a slot. And we also have an extended cyclic prefix for larger cell corresponding to 16.7 microseconds. LTE provides QPSK, 16 QAM and 64 QAM as downlink modulation schemes, so these can be assigned to the UEs in the resource allocations. So this picture illustrates a bit more the OFDMA time frequency multiplexing of several users. Again, the available bandwidth is organized in resource blocks of each 180 kHz, which is 12 subcarriers. So one UE can be assigned either one resource block, an example for this would be UE2, or multiple resource blocks, like UE1 has been assigned 3 resource blocks to transmit on. The subcarrier spacing is 15 kHz, and we can now see that each 1 millisecond these assignments can change. So the time domain in LTE is organized in subframes of each 1 millisecond, and one subframe corresponds to a transmission time interval. So every 1 millisecond we can change the scheduling decision, the base station can change the scheduling decision, and the distribution of the resource blocks among the users can change. Or it can also be maintained for the example of UE2. Now there's also the notion of a slot, which is 0.5 millisecond, corresponding to 7 OFDM symbols. The slot was introduced, for example, because the downlink reference symbols, also called the pilot symbols, are repeated every slot. So that's why it's also useful to have this notion of a slot. But for the resource assignment, again, the transmission time interval of 1 millisecond or subframe is the important part, because this defines the scheduling interval. So note that each UE can transmit with another modulation scheme. So depending on the radio link quality for each UE, either a more robust scheme like QPSK or a more sensitive scheme like 64 QAM can be assigned. Now let's have a closer look at the spectrum flexibility in LTE. We have seen that the physical layer supports any bandwidths from 1.4 MHz to 20 MHz in steps of 180 kHz, which is the resource block definition. But we've also seen that the current LTE specifications support a subset of 6 different system bandwidths for FDD and TDD, as they are also shown in the table. So this is these values of 1.4 up to 20 MHz, each corresponding to a certain number of resource blocks. The figure illustrates a bit more that the transmission bandwidths, which is actually then used in the downlink, for example, by the base station, is formed by the assigned bandwidths in terms of active resource blocks. The available channel bandwidth is a bit larger than the actual transmission bandwidth configuration of the cell, to leave some guard on both sides of the spectrum. Also important to note that all UEs must support the maximum bandwidth of 20 MHz, even though there may be smaller cell configurations available, and not all networks may support the 20 MHz depending on the spectrum that the operator has available. This slide shows the LTE frame structure type 1, which is the one for FDD operation, frequency division duplex. We have here the radio frame, which is defined as 10 millisecond, and that is the same definition as in wideband CDMA. One radio frame contains 10 subframes, and one subframe contains 2 slots. Now let's have a closer look to the subframe contents. So a subframe of 1 millisecond is illustrated here in this screenshot of a signal generator from Rohde and Schwarz. And as you can see here, this is a real signal. The x-axis is showing the time domain. So we see here an extract of 1 millisecond or 14 OFDM symbols for the normal configuration. And on the y-axis you have the frequency domain with 50 resource blocks, which is a 10 MHz signal. Now what is the contents of each subframe? In the beginning of each subframe there are certain control channels located, layer 1, 2 downlink control channels. So they for example, carry information about the scheduling decisions for the different UEs in a cell. So the UE would first read on these downlink control channels in order to get information whether there's resource assignments with user data inside the subframe coming up. So the actual user data allocations are represented in green on this picture. And you can see in this example that actually 2 users would share the available 10 MHz bandwidth, which is really just an example. You can also see at certain allocations downlink reference signals. And you can also see in this special subframe, which is the first one in a radio frame, that there's also certain synchronization and broadcast channels. So we have here in the middle in blue the primary synchronization channel, the secondary synchronization channel, and the physical broadcast channel PBCH, which are carrying predefined information important during cell search, which will be explained by Andreas in more detail later.
Christina, one question to the time plane showed by the signal generator. So what does it mean with the hashed area over the entire bandwidth? Can you explain that a little bit more in detail?
Yeah, of course. So the downlink reference signals, which are indicated here by the hashed areas, they are actually not transmitted over the whole bandwidth, over the whole 10 MHz in this example, but it's just indicated here the symbols which are carrying the downlink reference signals at specific locations inside. So it's specific subcarriers inside the indicated symbols here. So it is just for simplifications that we have hashed here these areas. And accordingly, this picture shows the LTE frame structure type 2 for TDD, time division duplex. The radio frame structure is the same also for TDD, that's 10 millisecond, subdivided into 10 subframes of each 1 millisecond. And we have also the notion of a slot of 0.5 millisecond. But of course, since it's TDD, there's a significant difference here, because in TDD we have uplink and downlink separated in the time domain. So this needs to be somehow reflected in the subframe structure as well. So let's also have a closer look at the contents of a subframe. So the table shows the possible uplink downlink configuration. So we have actually 7 different uplink downlink configurations defined for TDD. And as you can see here, it's indicated for each of the subframes of a radio frame whether it's carrying a downlink, denoted by a D, an uplink, denoted by a U, or whether it's a special subframe, denoted by an S. And you can also see that there's configurations with a downlink to uplink switch point periodicity of 5 or 10 milliseconds to select from. So let's have a closer look at one example. Let's have a look at the uplink downlink configuration 0, which is also shown in the screenshot again. So we have represented in the screenshot the 10 subframes, and so the subframe 0 would be a downlink one according to the table. So this is a downlink signal, and the green part is actually showing that there's user data in downlink carried in there. And again, subframe 5 is carrying a downlink data again. Then we have special subframes in subframe 1 and 6. The special subframe is actually carrying a downlink pilot time slot, a DWPTS, an uplink pilot time slot, a UPPTS, and a guard period. Guard period for TDD operation to switch from downlink to uplink. So downlink and uplink pilot time slot are used for regular data transmission as well. But they are just shorter because this special subframe has a specific configuration. Now the gray subframes which are indicated here in the screenshot, they are representing the uplink transmission. They are available for uplink transmission in this specific uplink downlink configuration 0. Also for TDD you have certain layer 1 and 2 downlink control channels defined at the beginning of each subframe, and you have also certain primary, secondary synchronization signals and a physical broadcast channel defined.